Hello everyone. So today we will discuss the nuclear binding energy. Before discussing this nuclear binding energy concept, first we have to understand the structure of an atom. So here an atom is given, it is the nucleus of the atom, and here are the orbits where electrons are revolving. If atomic number of this nucleus is Z, then Z represents number of protons. And if mass number is A, then A represents neutron plus proton. Then A minus Z represents the number of neutrons in the nucleus. So, nucleus is composed of Z number of protons and A minus Z number of neutrons. So, what do you expect? If you add Z, P means Z number of protons weight plus A minus Z N means A minus Z number of neutrons weight. So this weight you can call it as M. So you expect that this much be the weight of the nucleus, that is sum of individual nucleons. But in actual reality, when experimentally this weight is measured for the nucleus, this weight is always less than M. So weight difference, that is M minus M dash, this is delta M. So delta M is equal to M minus M dash is also known as mass defect. Mass defect of nucleus. What is mass defect? Mass defect means the weight of the nucleus is not equal to its individual nucleons weight sum. It is somewhat less than the weight of individual nucleons. This difference in weight is known as mass defect. This mass defect is converted into energy, that is delta M C square. You can say delta E. So delta E energy is equal to mass defect into C square. This energy is reflected, appears in form of nuclear binding energy. Nuclear binding energy. And this nuclear binding energy is utilized in holding these nucleons together within a very short radius of around 10 to the power minus 14 meters. This is the order of the radius of the nucleus. So within this short range, all the nucleons are tightly packed with the help of this energy that is known as nuclear binding energy. Nuclear binding energy is not criteria for stability. Criteria for stability of this nucleus is, this you can say as NBE. So only NB is not criteria for stability. So stability criteria, if you want to see stability criteria, that is NBE per nucleon. This is the concept. If this value comes around 8 or greater than 8 MeV per nucleon, then your nucleus considered to be stable. So let us understand with calculation of nuclear binding energy for oxygen nucleus. Here consider the example of oxygen nucleus. So its atomic number is 8 and mass number is 16. Then number of neutron will be 8 and number of proton will also be 8. So mass of nucleons, first we will calculate mass of nucleons. So it will be equal to 8 into mass of one neutron, that is 1.00866 plus 8 into mass of proton, that is 1.00727, and this comes 16.127488 MeV. So what you expect? You expect that nucleus weight must be this much. but actual weight of nucleus, it will be 15.99493 atomic mass unit. So this weight of nucleus is less than the actual weight of nucleons. You can say it as m dash and you can say it as m. So mass defect, that is mass defect delta m is equal to m dash minus m, and this value comes 0.13691 MU. If you convert into energy, that is delta E, this must be equal to 0.13691, and convert this mass into kg, that will be multiplication factor of 1.66 into 10 to the power minus 27. This is the conversion factor for atomic mass unit to kg, and multiplied by how much? C square, that is 3 into 10 to the power 8 ka whole square. And this value comes 2.045 into 10 to the power minus 11 joule. And this comes as 2.045 into 10 power minus 11 divided by 1.6 into 10 power minus 19, that is electronic charge. You will get the answer in electron volt, and that will be 1.28 into 10 to the power 7 EV, and convert it into an MeV, 1.28 into 10 to the power 2 MeV, and this is equal to 128 MeV. This is nuclear binding energy generated in the formation of this nucleus. Now we have to calculate NBE per nucleon. NBE per nucleon. This is NBE. And we have to calculate NBE per nucleon. So you will do nothing. Just divide it by number of nucleons. That is 128. And number of nucleons how much? 16. That is 16. And when you calculate, the value comes around 7.99 MeV per nucleon. So you see, this is under a stable criteria. Around 8 it is coming. Hence the nucleus of 1608 atom is stable. Same way, we can calculate the nuclear binding energy for all nucleus present in periodic table, and then we get a nuclear binding energy per nucleon curve and the stability of nucleus based on this curve predictions. So once you plot the nuclear binding energy per nucleon value against atomic number of elements, you get this type of curve. So here it is increasing atomic number, here NB curve is plotted. So what you observe here, in case of lighter nucleus or in case of heavy nucleus, NB per nucleon value is less compared to 8, and they are unstable. So what they do, lighter nuclei undergo fusion while heavy nuclei undergo fission. So during fusion process, two or more nuclei merge together and forms a new molecules, and number of nucleons in the nucleus increases. During fission process, it splits up into two lighter nuclei, and each nuclei have less number of nucleons. So they manipulate their number of nucleons inside the nucleus and form some new other nucleus. These nucleus comes in this zone, which is the stability zone of nucleus. Means the new nucleus formed during fusion or fission process, they have NB per nucleon value is around 8 MeV per nucleon. So the stability criteria is met. So lighter nucleus or heavier nucleus undergo fusion or fission process just only to produce stable nucleus, whose Nb per nucleon value is around 8 Ab. So that's all for today's video. If you like this video, please give a like button and please subscribe my channel. Thank you.